This video is to illustrate how the idea of an inverse function can be used to think about how equations are solved, and then transition into looking at inverse trig functions. So I'm going to start with a relatively simple equation, x plus 2 equals a third, and in one sense we can think about this as what input do I need to put in the function f of x equals x plus 2 in order to obtain the output 1/3. And so this idea of an inverse function sort of undoing what the function does lets us say off to the side that, all right, well, if f of x is the function that adds to undo that and get back to where I was, the inverse function there must be take away 2. And so, in a sense, what I'm doing when I subtract 2 from both sides is I'm just subtracting 2 from what I had. You know, the notation of f inverse of f of x is I'm putting, f inverse of f of x is I'm doing the minus 2 on the x plus 2, so that those go away. So I'm not going to show this for my other examples, but this is kind of the idea. I'm just going to be talking about it. So I'm going to subtract 2 from both sides, sort of undo that adding 2. So I subtract 2, and all of a sudden I've isolated the x. A third minus 2, that looks like 6/3, so negative 6/3 plus 1/3. And I get this negative 5/3, the actual arithmetic of figuring out what number I would add to 2 to get a third. So let's try this with another kind of a function, another equation. So simple 2x equals a third, and there the function is 2x, and so it's inverse. How do I undo multiplying by 2? I simply divide by 2. So I'm going to divide by 2, and that's equivalent to multiplying by a half. And so we get that the number I multiply times 2 to get a third, that's a sixth. So let me keep going. So the next one is a little bit more sophisticated. 2 to the x equals a third. And here we're trying to find out what do I raise 2, what power do I raise 2 to in order to get 1/3? And I realized that, oh, well, the inverse of 2 to the x is a log base 2 of x, and as much as that's not a very satisfying solution, I can log base 2 of both sides, and x is just the power I raised 2 to get a third, which is completely unsatisfying, and I can't even get an approximation on my calculator. So another approach is to just go, oh, well, the things that undo exponentials are logs, and I can log any old base, and then use the properties of logs. This is how I usually solve this kind of an equation. But the change of base formula is sort of an automation of these algebraic steps. Divide by log of 2, so that x is the log of a third divided by the log of 2. Well, that's what you get when you use change of base formula on the log base 2 of a third. So however you're solving this equation, it's still an inverse function that's getting at isolating or getting at that variable x. So I'm going to do one more example before I get to the trig. So this one's interesting in a sense because x squared is not an invertible function. And so when we go, oh, okay, well, I know how to undo squaring, it's take the square root. That really you're taking this function that is not one-to-one and restricting it to just one piece of it, the non-negative side, to get the inverse function. So, here's f of x equals x squared, and the inverse, the thing that undoes the squaring, f inverse, is the square root of x, but I had to restrict that domain to just be looking at non-negative numbers in order to make it one-to-one. And in practice, I don't necessarily think of that. I just go, okay, square root of both sides, and don't forget that there's two answers, that it's plus or minus the square root of a third. And so for the purists, I'm going to go ahead and rationalize. What the heck, rationalizing is kind of fun. But I've got two of these answers. I've got the square root of 3 over 3, plus or minus. In whatever application I'm trying to solve with this, I'll kind of know whether it's the positive one or the negative one, or maybe I need both for whatever reason. So trig functions are very similar to x squared in that sense. So let's say what I'm trying to do is find what value for x makes the sine of x equal to a third. And right off the bat, thinking graphically, so here's sine x, and I'm not drawing it on its entire domain, but there's sine x, and here's 1, and here's negative 1, and so I know that there are several places where sine x equals a third. I don't know where they are exactly. A third isn't the output, it's not the output for a special angle. It's not like it's sine x equals a half, which I could just know where it is. But I can see on the graph that there's many places where the output for sine ends up a third, and even on the unit circle, I can imagine several angles that have the y-coordinate equal to a third, a little bit less than pi over 6, because pi over 6 makes it a half. So when I think of an inverse function, it's got to be something that will undo this. And so let's just say that the inverse function, we'll call it arcsine of x, or some people call it sine inverse of x. I kind of like sine inverse of x just because then it's really clear what the heck you're doing. But, you know, go back over here and try to solve this equation. Sine x equals a third. And you say, oh, well, sure, that's just the arcsine of a third. And that's similar to saying that, what do I raise 2 to get a third? Oh, that's just the thing that I raised 2 to get a third. It's a very unsatisfying answer. And this one is even worse in a certain respect because it's only going to be one of the many answers. It happens to be the one that's shown right there. And so a big part of solving trig equations and understanding what inverses do is to really realize that I have to think of all the other answers, and I have to realize that the calculator is going to have to help me with this because I haven't really said anything yet. All I've said is what I was saying here, just in a different form, that it's the thing I take the sine of and get a third. So that's my introduction to inverse functions for trig.